All right, good afternoon, everyone. Welcome back. We got a little unexpected holiday on Thursday, didn't we? So we get set back a little bit. One class we lost, so we'll be having to make up ground. We'll just see how that goes. So I'm not going to change the calendar, the schedule at this point. Let's just kind of keep it the way it is, and we're just trying to catch up. So today, we're talking about 1.3. We're going to finish it up, make sure everyone understands the definition of the limit. Also using tables to find limits. And then we're going to move into 1.4, calculating limits. And then I think we'll have some time to talk about that fiber optic problem that I sent out. I asked everyone to take a look at, just kind of think about. Thursday, expect a quiz to start class. It'll probably be a Zoom poll that I send out with multiple choice. I'll put up the problems on I'll share my screen, show you the problems. It'll be multiple choice, and then you'll just fill out the poll. All right. And then homework, just remember that the homework, the homework is due for 1/3 and 1/4. What is the 31st? Is that Monday night? Yeah, Monday night. So this upcoming Monday, 11:59 p.m. Make sure you submit your handwritten work for 1.3 and 1.4. Also, make sure that it's all in one file, even though it's 2 sections. Make it one file, submit it through Canvas. And then I'll just look at it, review it, just kind of make sure you're, using correct notation, neatness. You're not just writing answers down, you're actually working through things. So yeah, and then our first exam is still a ways off. We have a couple of weeks, but I just want to remind you that it's Thursday, February 10th. All right. Okay, let's get started. Are there any questions before I start? Anything you want me to talk about? No? Okay, let's get down to business. So the first thing we're gonna do, make sure that we all understand what the limit of a function means, both the way we write it and then also what it looks like visually, because that's pretty much what we worked on last time, is the visual idea of the limit. So this is just to remind you that when you have a graph of a function here, the graph of the function f, when we write this notation down here in yellow, when we write down lim x with an arrow approaching, pointing to a, we say that limit x approaches a of the function f of x equals L. When we write that, what we mean is that as you approach a on the x-axis, from the left-hand side, the function, the y value of the function starts getting closer and closer to this value L. Also, when you come in from the right, approaching a from the right, the same thing happens. You're coming down on that function, the function's value is also approaching L. The important thing is to remember that what's happening at A is irrelevant, right? So I can have a hole here. That hole does not change the value of the limit. The limit is still going to be L. I could have my function be defined to be a dot up here. That has no impact on the limit. So limit means left and right headed to the same place. Got it? And that's the notation we use. All right. So in this section 1.3, there's problems within the homework that I kind of told you to avoid. And that's where they use a table to try and figure out the values of limits. So if I give you a picture, like last class, I gave you like a picture of a function, and we were talking about, they're in the notes. Let me bring up the notes. In the notes, I would give you these graphs and I would say, hey, think about, the limit from the left and limit from the right, and what's happening, blah, blah, blah. It's when we have the picture, it's kind of easy to look and see what the limit is, right? But what if we don't have the picture? So I want us to consider this function f of x equals sine x divided by x. And I want us to consider this limit x approaches 0 of this function. And the question is, what is the limit approaching? So remember also from last class that a limit does not have to exist, right? You can have a limit not exist. In order for the limit to exist, at least this limit, if I don't put a plus or minus on that 0, that means from both sides, I have to be headed to the same place, right? It is possible that that doesn't happen and we have like a jump in the graph. And in that case, we'd say the limit doesn't exist. Here, though, I'm asking for us to look at this function sine x over x and talk about what's happening as you approach 0 from both sides. And I'm not giving you a picture, right? So how would you go about doing this, right? If you didn't have a picture, you weren't allowed to use a graph, how would you do this? So what the book does is this: they make a table. So think about like a good old-fashioned t-table, right? You have x here, this is sine x over x, and you just start plugging in values for x. But we want to be getting close to 0. So we already know that, well, I hope that we already know that if I plug in 0, what would happen? If I try and just do the algebra, plug 0 into this function, I get sine of 0 over 0. And sine of 0 from pre-cal, we all know is 0. I hope we all know that. That's the y coordinate on the unit circle when your angle is 0. And that would be 0. So we get 0 on top, 0 on the bottom, and this is undefined. Right? It's undefined. So we know that you can't plug 0 in, right? But that doesn't mean that the limit is undefined. It doesn't mean that this limit doesn't exist, because the limit does not care about what's happening at 0. It cares what's happening close to 0. So we do this table where we plug in values. And the question is, what values do we plug in? Well, we want to be close to 0, right? So this right here is the table already filled out. First number I picked was -1. So if you think about a number line, right? Here's a number line. If this is 0, I can't plug 0 in, so I picked something close to 0. I'll come in from the left, -1, well, that's kind of close to 0, right? Kind of, not really, but if I plug -1 into this, so do sine of -1 divided by -1 on my calculator, I get my calculator out, do sine of -1 over -1, make sure I'm in radian mode. The calculator will spit out 0.84147909, blah, 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 all right? So I get that answer. Well, then I could get closer to 0. So I picked -0.5. So now I'm moving here instead to -0.5. Now I'm closer to 0 from the left side, and the calculator spits out 0.95885 something. And then I get even closer. So I pick another value, -0.1. And it spits out 0.99833. And then I get even closer, right? -0.001. Here's my answer. Do you understand what I'm doing here? I'm not showing the work, but you know, and I could keep doing this and get closer and closer and closer. All of those numbers are headed towards 0, but they're not actually getting to 0, and they're coming in from the left. And look at what the values of the function are headed towards. What are they heading towards? What does it look like? What are they getting closer and closer to?
1.
1, right? It looks like it's getting closer to 1. 0.84, 0.95, 0.998, 0.9999. So they do look like they're headed to 1, right? And then I want to come in from the right-hand side also. So from the right-hand side, what I do is I pick a number close to 0, like over here, like 1, plug it in, get this answer. Then I get closer, 0.5, then closer, 0.1. And I keep moving towards 0, right? From the right-hand side, this time of 0. And look at what those are headed towards. Same thing, right? They're headed towards 1. So this would make you believe that the answer to this is 1, right? That's what it looks like from the table. So the book, in the book, there's some homework problems where they tell you, hey, try and determine what the limit of this function is by using these values. So basically what they're providing you are the values over here to plug in, and then they're giving you some function, not this function, some other function. And they're asking you to plug those values in and try and see like a pattern of where the function looks like it's headed. Does that make sense when you get to a homework problem like that? Does it make sense what they're asking you to do? Yeah, I see a lot of shaking head, yes, okay. Now, I will tell you, I'm never going to test you on this, okay? because the point of this is to show you that this is tedious. Like, this is not an efficient way of figuring out what a limit is. We need a better way, all right? But this is just to get you to be thinking about what we're doing with the limit. We're taking values and getting closer and closer and closer and trying to figure out what the function's spitting out, all right? Trying to find like where it's headed. So it's more of an exercise than it is something that I'm gonna need to test you on, all right? All right, that pretty much covers the 1.3. The definition, I think we're clear, I hope. We're clear on the idea of what the notation means, that it has to be left and right, and then how we use a limit to finding limits using table values. And now we move into the very important, very, very, very important first real, like, okay, welcome to calculus. Let's test your algebra skills time. 1.4, calculating limits. So what this section is about is, okay, we've seen if I give you a graph, you should be able to get shown, like, tell me what a limit is. You can also, if I give you the function, you can use a table of values, but that's not very efficient. So do we have a way of calculating a limit if I don't give you a graph that is better than like that table of values? And we do, all right? We do have a way of doing it. So that's what this section is about, but it's gonna call on a lot of algebra skills. So let's scroll down here to 1.4. So this is basically me saying, like, yes, we know how to do it if we see a picture, but now we move on to the next part of this. How do we do it by hand? It's going to require a lot of algebra skills and tricks. All right, now before we can proceed into this, we have to establish what's called the limit laws. All right, now the limit laws are basically the rules that we have to play by. And in this class, Cal 1, we just give you the laws. We're not going to prove them. Okay, we can't do formal proofs in this class because most of you, I venture to say all of you have never taken a true like theorem proving course or like a logic course. So for us to try and prove anything rigorously would make no sense. So we have to at some point take some things on faith. These things we're taking on faith. These are the limit laws. These are the things you are allowed to do when you're dealing with limits. So I'm going to run through these. They're going to seem weird in the beginning, but let's just kind of look at them. And then as we work through some examples, I'll say, hey, look, the limit law, here's that limit law we were talking about. Here's how we use it, okay? So the first limit law says, the way to look at this is that if you have two functions being added together, okay, algebraically, two functions being added together. I can give you an example. Let's say we had x squared plus cosine of x. Those are two functions, right? You could look at them as two different functions. If we were trying to figure out what the limit of this was, okay, two different functions, we'll call this one the f function and this one the g function. If we were trying to figure out what the limit is of one of those two things added together, the limit law says that you can look at the limit of the first one and then the limit of the second one separately, and whatever the answers are, you add them together. So it allows you to kind of like, instead of focusing your attention on everything, if there's an addition sign between, you can look at each one and deal with each one. And then whatever answers you get individually, you put those two together and you add them. Now that may seem like an obvious thing, like, yeah, sure, that makes sense. But we have to have a rule that says we're allowed to do that. We cannot just assume that's true. The second limit law says the same thing, but with subtraction, okay? If you have two functions being subtracted, you can take the limit and you can look at them separately and then subtract the answers. Now, the third limit law says that if you're taking the limit of a c times f, so what I mean by that is this. Let's say you had 4 times x squared. You could look at this 4 as being multiplied in front as being a constant, and then look at this as being your function. The limit law says that if you're interested in knowing what this does as x approaches a, what you can do is focus all of your attention on this piece. Focus your attention on that x squared. Tell me what that does. And then whatever that does, just multiply that answer by 4. In other words, we can ignore the number in front. As long as it's a constant, we can just, I'm not going to say ignore it. We have to bring it in at the end, but what I like to say is the constant kind of comes for the ride. All right. It's not going to participate in the limit at all. It's just going to participate in at the end being tacked on to the front. So again, it just allows us to narrow our vision down to something, just the function. The next law deals with when you have multiplication between two functions. And this is a very nice law. It behaves exactly the way you would hope it would behave. If you have two functions being multiplied and you want to know what the limit is, you can look at each function's limit separately and then multiply the two answers. Limit law 5 is the exact same thing, except for division. If you have division of two functions and you want to know what the limit is, you're allowed to take the limit of the top and bottom separately. Okay, ignore, just look at the top, what is it headed to? Look at the bottom, what is it headed to? And then take the quotient of those answers. Now, we do have one restriction. The bottom can't be going to 0. If the bottom goes to 0, then we have division by 0. You'll see this play out again. It's always hard to read things like this without having examples, but we'll work examples and hopefully it'll come into focus for you. All right, there's only 32 more. No, there's only a few more, sorry. Number 6. So the limit law for 6 says that if you have a function raised to a power, right, that what you can do is you can just figure out what the function's doing, take that limit, figure out what happens, whatever that answer is, then raise it to the power. So it's almost like the limit can go in the power. Let me give you an example of this. Let's say I wanted to know what x squared plus cosine x all raised to the 7th power was. What if I wanted to know the limit as x went to 0, let's just say, all right? So I'm asking myself, what does this function do as x gets close to 0? This limit law says that you can focus all of your attention on this piece. Just tell me what this does. Whatever this goes to, let's say it goes to a number, whatever it goes to, take that answer, raise it to the 7th, and you're still good. Like you can just pass, you can pass this limit in through the power and not worry about the power until the end. Questions? I know this is weird just looking at all this without examples, but are there any questions right now?
I had a question about the previous one.
Yes.
When the denominator is 0, then does it just come out as undefined or does not exist? I'm sorry.
Well, it would, that's a great question. So the question that's being asked is, what if we're doing a limit and the bottom of it goes to 0, right? When we take the limit, it goes to 0. The question is, does that mean it just doesn't exist? Actually, that's a wonderful question, because that's kind of like what the heart of this whole thing is going to be about, is what happens when that is 0. And it's going to depend on a few things. The big thing it's going to depend on is, what is the top doing? We need to know what the top's doing, Ash. If the bottom is headed to 0 and the top is headed to 0 also, that's going to be a problem. We're going to have to work on that. But if the bottom's headed to 0 and the top's headed to, let's say, like the number 5, then something else happens. We're going to have these different scenarios. So good question. Stay tuned. We will have to deal with that. Yes.
Got it. Thank you.
Okay, the last limit laws here. The limit of a constant is a constant. Okay, so this one's easy to show. What if I did this? Asked you what the limit as x approached 5 was of 7. So what I'm asking you to do is look at this expression, the number 7, okay? Tell me what happens to the number 7 when I let x, oops, sorry, when I let x go to 5. Well, there is no x in here, right? 7 is 7. There's no x there. So x has no impact on the number 7, does it? So my answer should just be 7. That's what this limit law says. Does that make sense? It's like I'm asking you, how much does the number 7 change by if I let X go to 5. Well, that's not X, it's 7. It doesn't, there's nothing there to change it. Compare that to this one. This one's different. This one says, what's the limit as X goes to, let's say, 5 of X? So you hear the differences. This was a constant here in formula 7. It was a constant here, it's X. So what does this limit law say? If I ask you, what is X approaching as X approaches 5, what is it approaching?
5.
5, that's it, right? I mean, think about what I'm saying. Saying, hey, everyone, let X go to 5 and tell me what X does. It's kind of a stupid question. It's so obvious, it's ridiculous, right? It's like, what is X approaching if X is approaching 5? Well, 5, right? I mean, that's what it's approaching. This next one is the same rule as 8, but you can throw a power on it. So if I say, what's the limit as X approaches 5 of X squared? Well, we know that X is going to 5, right? So if you square 5, you get 25. Now, there's something you have to really keep in mind here, and don't lose sight of this. When we are doing limits, am I saying that X is equal to 5, that X is actually ever going to be 5? No.
No, just
right? It's approaching, getting close to. And we talked about this in the very first class where, we were talking about closeness. Are we close to one another compared to the sun, blah, blah, blah. Close is this real weird thing in this class. But in the limit, we are letting X approach 5. And X here, when I say equals, I'm not saying it equals 5. I'm saying it's getting closer and closer to 5. Here I'm saying as X approaches 5, X squared gets close to 25. It gets really, really close to 25. I'm not saying it ever gets there. I'm just saying it gets close to it. All right. The last two deal with square roots. So first one, or number 10 says, I'll give you an example of number 10 right here. If I do, what's the limit as X approaches 4 of the square root of X? This property says, oh, okay, we'll just take your 4, like X is going to 4. So this is approaching the square root of 4. So the square root of 4 is 2. So it's approaching 2. And the last limit law says that if you have a root of a function, the nth root of a function, you are allowed to just figure out what the function's doing first, figure out that limit, and then take the root after you do the limit. Okay. Now, that's all for the limit laws. We now have a very important property. Like, we need this to move on. It involves something called implied domains. All right, so before I even do this, I want to make sure you understand what I mean by an implied domain. Let's say I put a function up here for you. All right, there's a function. I'm just throwing this out there for you. Now, without me writing it, without me actually writing anything down, there's what is considered to be the implied domain of this function. Implied domain. The implied domain is basically the values of X that you're allowed to plug into this. I mean, there's certain values of X here I can't plug in, right? I mean, there are some values that if I try and plug them in, I'm going to have a problem. Can somebody give me an example of one value of X that you can't plug into this?
-1.
-1 wouldn't work. Would you all agree? Try and plug -1 in there. What happens? You get division by 0, right? Can't have division by 0. So without me writing it, it is implied that -1 is not in the domain. You're not allowed to plug in -1. There are other numbers you can't plug in though. Can you all see what they are? What has to happen with this in yellow? Because it's under a square root, what do you have to have?
Positive number.
It has to be positive. Now, can you take the square root of 0? What is the square root of 0?
0.
0. Okay, so you can take the square root of 0, right? But in
Yes.
this problem, we can't do it because then we would have division by 0, wouldn't we? So the square root alone just requires that our number underneath is not negative. But because the x plus 1 is in the denominator, we need basically that this x plus 1 is greater than 0, right? It has to be strictly greater than 0, because if it is 0, we have division by 0, not good. So this is our implied domain. If we subtract 1 on both sides, we get our implied domain right here. All values of x greater than -1. That is our implied domain. The implied domain is the domain, all right? It's the same thing, except I'm not writing it down. Every time somebody writes a function down, there is an implied domain. Okay, which means there's a domain that you would have to go figure out and make sure you understand what it is algebraically. So this, another way of writing this would be the set of all x such that x is bigger than -1. That's set notation. You could also write in interval notation, something like -1 to infinity. That would be like on a number line, right? If there's a number line, here's 0, here's -1. We're saying all values to the right of -1, not including -1, open hole there. That's a hole. Does this all look familiar? Stuff you've seen, algebra, pre-cal stuff? So every function, I appreciate everyone that, you have your cameras on. It makes my life so much easier when I ask a question and you nod and like agree or disagree, because then I don't, then it's not silence. It's actually, I can see responses. So appreciate that. So every function, when you're handed a function, has some implied domain. Sometimes it's all real numbers. Sometimes it's something like this, but we all need to understand that what it is, okay? That every function has an implied domain. Now that's important for this note. This is called the direct substitution property, all right? So the direct substitution property requires that we know how to figure out the implied domain of a function. So the property goes like this. If f, okay, so if f is our function, if it's a polynomial function, where did you study polynomial functions? College algebra, right? Those are the ones that look like little, roller coasters up and down. You had like polynomial functions that were either even or odd degrees. So you had like both sides go up, both sides go down, one side goes up, one side goes down. They have these curves. You try and find x-intercepts, right? This is all college algebra stuff. All those functions. So if your function happens to be a polynomial function or a rational function, that's another type of function you studied in college algebra, or a trigonometric function. Oh, you studied those in pre-cal, or an exponential function. Oh, you studied those in college algebra, or a logarithmic function. Okay, so basically almost all the functions you've ever studied, right? If f happens to be one of those, this property says that as long as a is in the implied domain of the function, we have that the limit as x approaches a of f of x equals f of a. Okay, what the hell is that saying? All right, I'm going to copy this. I'm just going to copy this part. Okay, super, super important here. All right. So as long as f is some function that we've seen in our lives pretty much, that as long as the a is in our implied domain, then the limit, the value of the limit, right? The limit is equal to the value of the function at A. So I'm going to give you an example. Let's say we wanted the limit as x approached 2 of e to the x plus sine x over x cubed minus 4x. Okay, now that looks like a freaking disaster. Let's do something else. Let's make it even worse. Let's do square root of that. Okay, that looks like a disastrous function, right? I mean, look at this thing. Square root of all this junk. I want to know what happens as x approaches 2. All right. No graph. We can't go look at the graph. Okay, we're not allowed to. All right, we can't look at the graph. We just have to look at this. So here's what I'm going to do. I'm going to first ask myself, is this function something that I've seen before in the past? Is it a polynomial, rational, logarithmic, exponential, or trig function? Well, not all of it together, but individually, the pieces are things I've seen, right? E to the x is an exponential function from college algebra. Sine of x is a trig function from pre-calc. X cubed minus 4x is a polynomial function from college algebra, right? And don't forget, the square root function is also a function that I've seen, yes? These are all things that look familiar. Now, if I start to think about the limit laws, the ones we just talked about, I see that I have this square root, right? This square root, come on. This square root I have here. The limit law tells me that I can leave the root out here and take the limit inside and just deal with the limit of the other crap and deal with the square root when I'm done. Do y'all see that that's that limit law allowing me to take the limit in the root? Y'all see that? I don't know exactly what law that was. Right here. That's the limit law 11. It allows me to push that into the root. And then do you see I have a numerator and denominator, right? I have two separate pieces there. There's a limit law that says that I can look at the top and bottom limits separately. So I can go further now and say, oh, this is equal to the square root of the limit as x approaches 2 of the top numerator over the limit as x approaches 2 of the denominator. Okay, so I'll label this. This was limit law. I'm going to say LL11, right? Number 11 got me there. And then limit law, which one is it here? 5 allows me to split a fraction into a limit on top and bottom. So this right here was limit law 5. Now this was only allowed, this limit law 5 was only allowed, and Ash brought this up earlier, as long as this bottom one doesn't go to 0, which I think we can do a quick check. If I let x go to 2 here, this goes to 8. Oh shit. Sorry, I randomly made up this problem. Okay, everyone, we have to fix it. What are the chances that I would make one up that would just go wrong? Make that a plus there. Sorry, everyone, make that a plus 4x. I don't want it to go to 0. I do not want it to go to 0 on the bottom. Please change that to a plus right there. So as x approaches 2, do y'all see the bottom does not go to 0 now? Don't ask me what would have happened if it went to 0. We're not ready for that, okay? That was unintentional. So I've split it up. Now, at this point, I'm almost ready. I'm going to split the numerator up into 2 limits. Do we have a limit law that allows me to do that? Is there a limit law that allows me to take this addition and split it into 2 limits?
Yes.
Yes, right. That was, I think, the first one, wasn't it? Yeah, very first one. Very first one. So I'm allowed to split that one on top, and on the bottom, I don't need to split this because this is a polynomial, isn't it? By itself, it's a polynomial.
Yes.
So I'm just going to leave it. x cubed plus 4x. And now at this point, I've used all these limit laws to get me here. Now I'm going to use the direct substitution property. This right here. I'm going to use this now. So as long as where we're approaching is in the implied domain of the function, we're in business. So when we look at the function, when we look at these functions, when we look at these functions, right? E to the x sine x, x cubed plus 4x. Can we plug 2 into all of these? You see any problems? See any division by 0 or any other issues? There's no issues, right? No issues at all. You can replace that x with 2, replace that x with 2, replace these x's with 2, and this should be our answer then. Square root. So at this point, I no longer have my limit. I'm letting x go to 2. So the top left is headed towards e squared plus this is headed towards sine of 2. Whatever it is, I don't know what sine of 2 is. And then all over, let's see, 2 cubed plus 4 times 2 is 8 plus 8, that's 16. The direct substitution property basically tells you this. As long as you don't have any domain issues, taking the limit is equivalent to just plugging the number in for x. Let me say that again. The direct substitution property is saying that when you're doing a limit, so long as the number you're approaching is in the domain of all the functions in there, then all you have to do is plug the number in for x, and that's your answer. You just direct substitute the value of x in. Let's do one more. I won't go through all this detail. I'm going to do it a lot faster. Watch. Let's say we have limit x approaches, let's go with 5 of x squared minus 2 over x plus 1. All right. So what I'm going to do right now is I'm just going to check to make sure that when I plug 5 into these, I don't get any issues. All right. So I'm going to do like a direct substitution of 5 in for x. If I replace this with 5, I'm doing some red. I'm just going to kind of say like, what happens? Well, 5 squared would be 25 minus 2 over 5 plus 1. That's 6. So this is headed towards 23 over 6, right? There was never an issue with division by 0 or square roots of negative numbers or any domain problems, right? 5 went in nice and smooth and easy, nothing bad, right? Nothing bad. The direct substitution property says you're allowed to do that, and this will be your answer, and you're done. Okay, you are done. That's your answer. So I'm going to illustrate this. I'm going to illustrate this real quick by graphing that function for you. Let me bring it up over here. Let me type it in first. I'm going to graph x squared minus 2 over, no, over x plus 1. Okay. And where were we approaching? We were approaching what x value?
5.
5. Okay, so let me just put x equals 5, and I'm going to make it a dotted line so you can kind of see it there. So we were approaching an x value of 5 and from the left and from the right. And what was our answer? 23 over 6, something like that. Let me show you where that is over here. Y equals 23 over 6. There it is, right? That's 23 over 6. So you can see from this that as we are approaching, x was approaching 5 here from the left and right, our function's y values were also approaching that value here, which is 23 over 6. See, but we didn't need the graph to see that. Do you understand? We did it just algebraically by just replacing the x with 5. Okay, I have bad news. All right. Does that seem easy to you? Like just plug in the number? But calculus would be easy if that was all you did, was just plugged in the freaking number, okay? That's not what we're interested in at all in this class. But we have to establish that property. We have to make sure that you understand that if there are no problems, you just plug the number in for x and you're done. If there are no problems, we are interested in when there is a problem like this, okay? So all of that was just to tell you, we have that now, right? Like we have that property, good for us, but what about this? What if I have a limit like x approaches 2 of x squared minus 4 over x plus x minus 2? So what if I have that? Well, the direct substitution property says that as long as I don't have any problems, I can just plug in the number for, just replace all my x's with 2's, right? That's what it says, so long as I don't have any problems. Now, individually, the numerator, can you plug the 2 into the numerator? Right, it's a polynomial, right? Just plug in 2, you get an answer, right? The denominator is also a polynomial. You could plug 2 in, you get an answer, big deal. Well, the problem is that when you try the direct substitution in the numerator, what do you get?
0.
0. And what do you get in the denominator?
0 as well.
0. So that means it's undefined, right? Direct substitution will not work here because we have this issue of division by 0. That is causing a problem. So direct substitution is off the table now because 2 was not in the implied domain of that function. Are we clear? So what's the answer? Do we say then that the limit does not exist? Can we say that by, all we tried to do is plug in 2 and it didn't work. But does that mean when I graph this function and we get closer to 2 that the function doesn't have a limit? Would y'all like to see the function? Of course you would. Let me graph that function for you. It was x squared minus 4 over x minus 2. 2. There it is. There's the graph. Where were we approaching? 2, right? We were approaching 2. Okay, here's 2. Now check this out. If I approach 2 from the left or from the right, is the function headed somewhere?
Yes.
Does it look like it's headed somewhere? What does it look like it's headed towards?
Toward 4.
It looks like it's headed towards 4. But how in the world would we have known that with that, right? Do y'all understand, like visually, when you look at the graph, the answer is 4, but how do we know it's 4 from this? From this, all we get is 0 of 0, so we have a problem, yes? We have a problem. So that's what this 1.4 is about, this section. It's about if you have this limit right here, and you're getting something like this, can you still get me the correct answer? All right, so how are we going to do it? How are we going to do it? Well, here's what we do. Anytime you have a limit from here on out for the rest of your life with calculus, anytime you have a limit and you try direct substitution and you get 0 over 0, 0 over 0. So you take the limit, all right? Understand, this is when you're taking the limit and you're letting x go to some number. If you get 0 over 0, I want you to think this, that this is bad, okay? This is bad, and that it means you're going to need some sort of algebra, or you're going to need some sort of trick to get around this, all right? So say it again, because someone's going to mess us up. From here on out, when you're taking a limit, if you get 0 over 0, it's bad and you need algebra. Do not take a limit, get 0 over 0, and tell me the answer is undefined. Someone's going to do it. Someone's going to, on a test, is going to get 0 over 0 when they take a limit, and they're going to tell me undefined. And out of 10 points, I'm going to give you nothing. Nothing, no partial credit. That is the worst mistake you can make, because that is exactly why we're here. Okay, we are here to find our way around that problem. Okay, we want to be able to get the answer 4 here, not undefined. You with me? So let's do it. Okay, let me go back to that problem. Let's do it. So I look at this problem. And I say to myself, okay, I know already this gives me 0 over 0, right? This we know goes to 0 over 0. This is bad. This is an algebra or some trick. Well, I do know some algebra here. I see something I recognize from my good old days in college algebra, The numerator is a difference of squares, right? X squared minus 4 can be written as x plus 2, x minus 2. And the denominator is x minus 2, right? I mean, that's just algebra. And x minus 2 is a common factor, so you're allowed to cancel this. Now, I'm curious. I want to know something. I'm going to do a poll real quick. It's going to just be a yes or no question. I'm curious. How many of you in college algebra, when you took college algebra, remember that your instructor told you that when you have an expression like this and you cancel these factors, that you have to promise me, there's a little asterisk here. When you do this cancellation, there's an asterisk, that you're promising me that x will never be equal to 2. Anytime you cancel factors, you have to promise me that you're never going to let x be a value that would have made it 0. So like 2 makes both of these 0, right? So if you cancel those, you got to promise me from here on out that x can't be 2. That's usually not stressed in algebra. So if you didn't, it's okay. I'm just curious. Like I beat that through my students' heads. Like every single time I cancel something in my 1414 class, we put an asterisk and like make a promise. And the reason is because right now in calculus, you have to understand that we're canceling these and we're making a promise to ourselves that x is never going to be 2. From here on out, x can't be 2. Okay, so about 80% of you, that was not stressed. Okay, good. So I'm stressing it right now. Anytime we cancel factors, you're making a promise. It's like that little asterisk at the bottom of a contract that you need to read, right? That's kind of what this is, a little asterisk. Okay, so from here on out, I'm allowed to do that. I am allowed to cancel. Let me end the poll. I'm allowed to do this cancellation so long as I promise you that x will never be 2. So here's where I am. I've canceled the factors. I have x plus 2. Now, looking at this as a new problem, can I do direct substitution into that now? Yeah, Nico's saying, yeah. I mean, that's just a polynomial. Just plug 2 in, right? Plug 2 in. And so the answer should be 4. But wait a minute. I just thought I told you you can't plug 2 in. What the hell? Oh, because I'm not telling you to plug in 2. What does the limit mean? Am I telling you to plug 2 in? No, I'm telling you to let x get really close to 2, as close as you ever want to go without ever actually being 2. So 1.9999999, or even closer if you want. And so our answer, what we're saying is that our answer function is getting closer and closer and closer and closer and closer to 4. It will never get to 4 though. In this case, it never gets to 4. So when we look at our picture, and this is one of the big drawbacks to graphing calculators, what actually lives here on that red graph? What is actually happening right there at that point?
Nothingness.
Nothing. So it actually should look like this. We should have right there a hole. That is technically what is really happening on this graph. And I can't I told y'all, I'm going to talk about this a lot in this class. Technology has come so far, like from when I was a student to now, just night and day. Even in the last 5 years, like what you can do on the computer with graphing, it blows my mind. But I do not understand still why they haven't figured out how to just put a freaking hole where there's a hole. I mean, there's a hole in this graph, and it's very misleading, right, to not have it there. Because it makes you think that this is a solid line. It's not a solid line. It's that, okay? So as you approach from the left, you're approaching 4. As you approach from the right, you're approaching 4. You will never get to 4. But you're approaching it. You're getting closer. All right. So for this problem, we had bad situation, 0 over 0. It required that we knew difference of squares. Yes? So that's some factoring. It's algebra. Ready for another one? Let's do some more examples. I've got a whole bunch of examples here to do. How about this one? The first thing we're going to do is try direct substitution. So I'm just going to kind of get a feel for what's happening if I try and just replace the x with 1. So on top I get 0. 1 cubed, right, is 1 minus 1, 0. On the bottom, 1 minus 1, 0. This is bad. I need some algebra. I need a trick. I need something, right? That's the only way I'm going to get around this. Does anyone want to volunteer to be the person who's going to get this wrong on the test? No? No? That's going to tell me undefined. Thank you, Kevin. Appreciate it. Yeah, I mean, I keep saying that because I really hope nobody does, all right? But inevitably, I don't think I've ever had a semester where someone doesn't give me undefined here or something on a test. This is going to be the semester, though. I feel it. This class, and you're all going to be the ones. Okay, here we go. I need some algebra. All right, well, it's now up to you. It's now up to your algebra skills. So does anyone see anything here algebraically that you can do? And all algebra is fair game. Like anything algebraically that's correct and technically like right, you're allowed. So I have not called on anyone today because I've just been yapping away here. So I'll take a volunteer. Anybody recognize what that is? What was the previous problem? Previous problem was a what? I factored it, I called it a what?
Difference of square.
Difference of squares. What is that?
Binomial.
It is a binomial, but it's special. It's special. It's a difference of
Cubes.
cubes. And there's a formula for that. Just like the difference of squares has a formula, the difference of cubes does also. Now, if you don't remember it, it's okay. You don't remember. You just need to know that there is a difference cubes formula. It is on your formula sheets, and it's under the algebra section right here. Factoring special polynomials, right there. X cubed minus y cubed. This one right here is what you need to at least know exists. All right, I'm gonna bring it in here for us. So I need to know that formula exists. And so what we basically have here is like x cubed minus 1 cubed, right? Isn't that what we really have? X cubed minus 1. So it's like wherever the x is will stay x, and wherever the y is, we replace it with 1. All right, so with that said, let's start out with, let's go with James. James, what do you got going on today?
One more time.
What's that?
Sorry, you said what do I got going on today?
Yeah. What's up, James?
Well, you know, Tuesdays are busy.
Yeah. How do you feel about, can you rewrite this x cubed minus 1 using this formula? Do you feel like you could tell me what to put in here?
X cubed. Yeah. So it would be x minus 1,
Okay,
then x squared
good,
plus x
good.
plus 1.
Boom,
Right?
we're done. Yep, excellent. Okay, that is the formula right there. That's applying the difference of cubes formula to the thing we had. Now, I'll be honest with you. You want to be in Cal 2, you want to be an engineer, you need to know that formula. Okay, it's not something you need to be looking up. I'm not saying you need to know it today, but you need to know it by the time you get to Cal 2. You better be good enough with your algebra to know difference of cubes formula, because it should be automatic at some point. All right. It takes time, but I'm being honest with you. I'm never going to lie to you and try and paint something the way it isn't. All right. It's trying to be real to you. You have to go to a university, compete, right? Compete with other people who want to be engineers just like you, or computer scientists, right? So you have to, there's certain things you need to know, and that's one thing you need to know. Okay, good, James. You did great with that. X minus 1. Okay, x squared plus x plus 1. And then all of that is over 1 minus x. So the theme so far has been, if we get 0 to 0, we're doing some sort of algebra. In this case, we've done factoring twice, haven't we? It's twice we've done some sort of factoring. Now, if we have any hope of getting around that 0 over 0, we have to somehow eliminate this 1 minus x from being a division by 0, right? That's what's causing the problem. And do you all see that in the numerator, we almost have a 1 minus x? We don't, though. We have x minus 1. And those are not the same thing, are they? They're not. But Christian? Is Christian here? Christian? Wait, Bellum, were you going to say something?
We have to put like a different symbol, no? Like a minus to make.
Okay, good. I'll let Bellum do that. Okay, good. You're recognizing that in order to make those two the same, you have to rewrite this by factoring a -1 out and writing it as negative x plus 1. Is that what you're saying, Bellum? Something like that?
Yes.
Okay, that is an algebraic thing. It's a little trick, a little skill that you should know, that if your factors are off by a sign, right? If they're off by a sign, you can always factor out a -1. Do you all agree that negative x plus 1 is now the same? Because I could rewrite that as 1 minus x with a -1 in front. Like these two are the same thing. The following? Algebraically, same thing. Now they cancel. And this is where there's that little asterisk. I need to promise you x can never be 1 when I do this canceling. Rewrite limit, x approaches 1, what was left? Well, I had the negative, right? Don't forget that -1, it's still here. And then we had the x squared plus x plus 1 in parentheses. Now try direct substitution. Let x go to 1. When we let x go to 1, notice I'm not going to write the limit anymore. I'm just going to let x go to 1. And I get -3 as an answer. How are y'all doing? All right. The algebra is, we're just lifting off right now with the algebra. We're just cleared wheels off the ground. Now, I mean, now we're going to start to get into more serious algebra. All right. Let's just verify, if you don't mind. I'm going to graph this function. It was x cubed minus 1 over 1 minus x. And we were letting x approach 1, right? So here's the graph of this. We're approaching x is 1, and you can see the function's value from the left and the right is headed towards, hey, -3. Isn't that what we got? That's what we got, right? Okay. Again, the computer fails to show us the hole. There is a hole here. It's not showing it to us because for some reason, I don't know why, they haven't figured out how to do that yet. Okay. So 1.4, we are calculating limits by hand without any picture. By hand, we're figuring out what a function is doing. All right, next one. Do y'all have any comments right now? How's this making you feel?
Is always like the best practice is to take whatever the limit is going to and plugging it in initially.
Absolutely.
Okay.
Yes. So what you do on anytime you have a limit is you just take whatever x is going to, plug it in, and see what's happening, right? If you get something like, I don't know, let's say you get 1 divided by 4, then your answer is 1/4, and that's it. You're done. The only thing that we're interested in, or what makes calculus interesting, is when we get something like 0 over 0, or some sort of division by 0, and that's where the calculus is going to be born from. It's kind of like, well, yeah, I don't want to get ahead of myself. What you said is exactly what you need to do. Every single limit you ever have, just plug in, see what happens, and then from there, you know, go down whichever road you need to go down. So let's do that. It was red, right? Is that
Yeah,
Red. Okay, so let's do that here, Red. If you go and just plug 0 in, tell me what you get, Red. I didn't hear you if you said something.
isn't it 0/0?
0/0. And Red, when you see 0/0, what are you thinking?
Use algebra
Algebra or some trick,
or
right?
trick. Yes.
That's it. It's bad. All right, that's bad. In your Canvas, in Canvas under course files, you are going to find this file right here. I call it the limit summary. Does that look familiar to anyone yet? Because I did put it in your files. This right here is basically a summary of what we're talking about today. If we ever see 0/0, what do? You use algebra or some trick, okay? That's where we are right now in this class. If we ever see 0/0, we're gonna do algebra or some trick. I think from looking at this little cheat sheet thing, you can see we have a lot of shit to do still. We have to look at all these different scenarios, all of these different things that could happen and what we do and how we handle them. We are just at the tip of the iceberg here. We're only dealing today with this situation. I have not shown you this sheet yet because we're not quite ready for it yet. We're just barely getting in it, but I want you to know it's there. All right, so you will have something to refer to kind of remind you what to do. All right, so 0/0 algebra, here we go. Thank you, Red, for asking question. I'm gonna check you off here. Did I call Christian? I did call Christian, yes, no? Was it Christian?
Here.
No, who did I call? I called James.
You called Christian, but then Belem answered.
Oh, that's right, that's right. Thank you, thank you. Red, there's Red, and then, oh, there we go. All right, we're good? So in the previous two problems, we factored. We used difference of squares on the first one. We used difference of cubes on the second one. And for this one, what do you do? Right? Do y'all agree there's nothing natural here that just kind of is like staring at you going, oh, please factor me, you know? No difference of squares, no difference of cubes. Do y'all see that? Nothing obvious. So this is why it's so important in Cal 1 that when you start working these problems, well, it's important for me to stress to you that I'm now about to start to show you tricks. They're not tricks, they're just things that you can do algebraically that might make your life better. So whenever you see a square root, like you see that square root there, the thing you should be thinking about is this. And again, it's not always going to work, but you want to try it. I'm going to multiply this by 1. Okay, but the one that I'm going to pick is going to be very clever. You ready? Here it is. The square root of x plus 1 over the square root of x plus 1 plus 1. Does anybody know what that's called? When I take an expression like this and I rewrite it, but I change the sign in between from a minus to a plus, or if this was a plus, I change it to a minus. Anyone know what that's called, this thing? No? The conjugate. I am multiplying the numerator and denominator by the conjugate of the numerator. Right? Do you all agree that's not very natural? Like that's not something you just be like, oh yeah, sure, just do the conjugate, you know? But now you know that when you have square roots, you might start thinking about a conjugate. Let's see why. Let's see why. I'm now going to multiply out the numerator. That means I've got to expand that, which means I have to like FOIL it. So when I go from here to here, what do I get, Kevin? Where's Kevin? Kevin answered. Technically, Kevin answered. Kevin volunteered to be the first one to mess up that problem. So Kevin, I'll give you the option of deferring this to a classmate, or do you want it?
Hey, just saying I'll do something, answering something, so I'll try it out, so.
Okay, all right. So when you take a root, right, root x plus 1 times root x plus 1, what happens?
You get the root squared.
That's right. You get the root squared. And when you square the root, what happens? When you take a
It
square root and
becomes
square it,
X, yeah, it becomes what's it squared to, so it's x plus 1.
just x plus 1, right? That's what happens there. The roots go away and you just get x plus 1. Okay, great. Now, something very special happens on the next two multiplications. What happens on the next two? When I go here to here and then here to here.
You get the regular squared x plus 1 and negative squared x plus 1.
Which does what?
Cancels out and makes 0.
Cancels. Exactly. Anytime you multiply a conjugate, something times its conjugate, the middle two multiplications will always cancel each other out. Which means I don't have to worry about the middle two or the second two multiplications. I only have to consider myself with the last two multiplications, which is this one. Now, I will put it here just so y'all see it. The second multiplication would have given me square root of x plus 1. The middle one would have given me negative square root of x plus 1. And those two are going to kill each other off. Guaranteed every time when you have a conjugate. Which is why we do the conjugate, all right? And then the last multiplication would be just negative 1, wouldn't it? That's when you do the negative 1 times 1?
Yes,
Okay,
which would cancel out with the other one and just make the top x.
that's right. It's going to make the top x, which I'm going to rewrite the bottom. Now, I haven't done the bottom, right? I'm supposed to multiply the x through like this, right? I'm supposed to do that? Don't, okay, don't. Do not push that x through. Leave the x there and leave this denominator like that. Do not push the x through. Kevin pointed out that the numerator, the ones canceled, which leaves us with just an x on top. Then we have the x on bottom, then the square root of x plus 1 plus 1. Questions on that algebra? What happens now?
The x's cancel out.
The x's cancel. Now, up top, we have a 1. Don't forget, when you cancel that x, there's still something up there as a 1. And also, there's a little asterisk here. You promised me that x can't be 0. Because if x is 0, then that's undefined. But we're taking a limit, so we're not worried about that. We're letting x approach 0. So we are at the final step here. I have limit, x is approaching 0. The numerator is a 1. The denominator is the square root of x plus 1 plus 1. Now let's let x go to 0, approach 0. So when we do that, we get 1 over square root of 0 plus 1 plus 1. That gives me 1 over 1 plus 1, which gives me a half. There it is. Hey, Christian. Where's Christian? Christian.
Yes.
Hey, Christian, I have a question for you.
Mhm.
When did I stop writing the limit? Like the entire time I was writing limit, 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 and then here I stopped. Why did I stop writing the limit there?
Because you didn't.
What did I do in that step, Christian? What did I actually do in that step?
Direct substitution.
Yeah, I did direct substitution. That's when your limit goes away, okay? So everything is limit, 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 until you actually let x go where it's going, and then you stop writing the limit. I expect that when I see your work, okay? If you don't write the limit, it's wrong. And if you keep writing the limit too long, it's wrong. You need to understand what's happening here. everything in every one of those steps, all of those steps right there are all algebra. You don't have to be a calculus student to do all of these steps. The calculus step is right there, taking the limit. That's the calculus step, all right? Questions? Conjugate. When I see square roots, I'm thinking conjugate. How do you think you get good at this?
Practice.
Practice, practice. You got to do a lot of limits to get comfortable. All right, let's do, why don't I give you a moment to just first do direct substitution here. You always need to do that direct substitution first. You're letting x approach 2. Do we all agree 0, 0? Bad. Algebra time. All right. Let's see. Landon? How's it going, Landon? You there?
It's going good. I'm a bit confused on like the upper part of the equation, how you can like get it to substitute with the x minus 2 on the bottom. So that's what I'm trying to look at right now.
Yeah, but you said something very important in what Landon just said. I want everyone to pay attention. Landon said, I'm trying to basically figure out what algebra I can do to make the x minus 2 on the bottom cancel, right? Pretty much that's what you're getting at?
Yes.
Because we know that the problem here is that this goes to 0 and we're trying to get rid of it. And the only way to get rid of that is to make the x minus 2 cancel. In the previous problems, that's what we've done. On this one, the x being 0 on the bottom was a problem. So what did we do? Right here, we got rid of the x, right? We canceled it. On the previous problem, what was the problem? Oh, the 1 minus x gave us division by 0. So what did we do? We canceled it right there. The one before that, what was the problem? Oh, the x minus 2 is the problem, right? What did we do? Oh, we canceled it right there. So that's kind of like the theme of what we're trying to do. We're trying to get the x minus 2 to cancel somehow. So that's very good observation, Landon.
Thank you.
How the hell are you going to do it though, right? I mean,
That's the thing. Yeah,
how do you do it?
Not really sure.
So let's do this, Landon. Let me walk you through this. Up top, you have 2 fractions, right?
Yes.
Is there anything algebraically that you can do to those 2 fractions to maybe make them look a little bit better?
You could probably what should we call it? You could probably do the same thing for the last equation, right? Where you where you multiply both the denominator and the numerator by the same thing in order to actually get x.
Like the conjugate thing, you mean?
Yes.
Okay, so could we? Yes, we could multiply by the conjugate. We could. Now, will that get us there? I don't know.
Yeah.
Okay, and that's one of the weird things about calculus is that the algebra, you can do anything you want as long as it's legal to do algebraic. So you could try that, but I can tell you from my experience, it's not going to work. What would work better, Landon, is when we see 2 fractions like this, that we combine them together into one fraction.
Yeah, that's what.
Okay.
Yes, that makes sense.
Let's try it. Okay, let's try it. Let's try and combine these 2 together. So we just get a common denominator, right? We just multiply this one by 4 over 4 and this one by x squared over x squared. I'm getting a common denominator so I can squeeze these together. That leaves me with 4 minus x squared over 4 times x squared. So this is a scratch work step I'm doing on the side.
Okay,
This is just taking two fractions and putting them together with common denominator, which I would hope in a Cal 1 class is not too much to ask.
Hmm.
If it is, that's where you make a little asterisk, a little note, and you meet me in my office hours. We make sure you know how to put two fractions together. So that allows me to rewrite this as limit x approaches 2. Now the new numerator is this. And then the denominator was still this. All right, Landon, that makes sense?
yes, it does make sense.
Okay. Do you see it now?
Kind of.
Okay, what do you see?
I see something, but I really can't describe it.
What is this?
Yeah,
Landon?
that it is a it is something that you can, I forgot how to say it, but you can split that into two separate
Yes.
equations. Yes.
Two separate factors. Yeah, you can
Yes.
factor that. It's a difference of squares, right? That is a
Yes.
difference of squares. And so it factors. So let's try to factor that. Equals limit. See, I'm still writing the limit. I just love writing limit. It factors to be 2 plus x, 2 minus x. It doesn't matter which order. You could do 2 minus x, 2 plus x. That's irrelevant. It's multiplication, so the order doesn't matter. Is that all right, everyone?
Yes.
Did that help?
Yes, it did. Because now you
How?
can you can multiply both the top and the bottom by 4x squared to
Okay.
get rid of the fraction on top.
So if I multiply this by 4x squared on top and bottom, it'll appear down here, right?
Yes.
Okay, I agree. Again, that is an algebraic move we can make. Pause that though. Just hang tight on that. Do you you mentioned, Landon, that you really wanted the x minus 2 to go away, didn't you, in the beginning?
Yes.
Okay, do you see that it can right now, almost?
Yes, it can almost.
With what? What can it-
With a 2 minus x on top.
Okay, everyone see that right there? That 2 minus x is almost x minus 2. Almost. I would need to take this 2 minus x, factor -1 out of it, and then it would become -2 plus x. But that's the same as -1 times x minus 2. And now they're the same, aren't they?
Yes.
Okay, I'm gonna come back to that. I'm gonna erase it because I want to come back to that. Actually, let me do it this way. I want to do one more thing before I get to that. Okay, here's what I'm going to do. And this is hopefully will help everyone. I'm going to rewrite this bottom piece as x minus 2 over 1. That way it looks like I have a fraction over a fraction. You all see that? Fraction over fraction. The reason I'm doing that is because whenever you have a fraction divided by a fraction, it's the same as taking the top fraction and instead of dividing it by this, it's equivalent to doing multiplication of what?
The
Division is
reciprocal.
the same as, good, red. Division is the same as multiplication of the reciprocal. So I can multiply this by 1 over the x minus 2. These are equivalent. And that's to help you see that these two will indeed cancel. But you still have to pull that -1 out. So let's pull that -1, make this an x minus 2, and then cancel out the x minus 2. And now we have achieved what we were hoping to achieve, which was to get rid of that x minus 2. I'm not ready to actually take the limit yet. I'm not ready to let x go to 2. I'm just going to kind of clean it all up. I have a -1 on top of 2 plus x. Those are the only things that were left up here. Well, there was a 1 there too. And then on the bottom, the only thing left was just the 4x squared, right? That's the only thing on the bottom. Let x go to 2. Now we let x go to 2. No more limit. Negative 2 plus 2 over 4 times 2 squared. So negative 4 on top, and on the bottom, 16, negative 1/4.
I have a question.
Yes.
So it's possible after we did what we just did, and when we replace the x and get 0 over 0 the second time?
If you do everything we did and then at the end, let x go to 2 and you still get 0 over 0, something's wrong.
Okay.
Is that what you're asking me?
Yes.
Okay, yeah, something is wrong. That means you didn't get the right thing to cancel. Something didn't happen that was supposed to. Okay, it's 2:22. We still have a little bit of time, but let me just kind of back up. Okay, when we're trying to find limits mechanically like we are right now, started off, we had a difference of squares. First problem required, we knew difference of squares. Second problem required difference of cubes. Third problem required a conjugate with a radical. The fourth problem has required that we combine 2 fractions into 1, and then within that, we had to do a difference of squares and factor out a -1 to make things cancel properly. Do y'all see how this is like the algebra? Do you see that it's just like this is what makes this hard? Is your algebra has to be good. All right. If your algebra is no good, then this becomes very tough to do. All right, let's look at another one. Oh, you know what I wanted to do on this one? I wanted to graph this one. Just again to kind of just show you like what we're doing is working. It was 1 over x squared minus 1/4. It was all of that. Oh, no. It was all of that divided by x minus 2. Yeah, and we were approaching 2. And so what you don't see here is there's actually a hole because you can't plug 2 in. There is a hole here. So as we approach 2, this is 2 right there. As we approach 2 from the left and right on this function, there's a hole there, but we just determined that we are headed to some value over here, and we got negative 0.25, didn't we? Or negative 1/4. And you can see that's exactly what's happening here. Yeah, there. Trying to get negative 0.25 to show up. There we go. There we go. There's the graph. As we approach it from left and right, the y value is headed to negative 0.25. So I know you might be sitting there going, well, wait a minute, does this mean I can just like graph these and I get the answer and then I don't have to do all the limit stuff? And like I said, technology has come a long way. So, you know, this was not available to people hundreds of years ago, right? And that is one thing that I think we kind of lose sight of with math and calculus. It's like, you know, you want to become an engineer, you know, computer science, whatever your major is, right? And you take a math class and you're like, well, when am I going to use this later and all this stuff? You have to remember that what we're doing when we study calculus is we're studying, it's like taking a history class and you're studying like, you know, North American history, right? Like you were just talking about the history of North America. Calculus is basically saying, hey, look, over the period of like thousands of years, human beings were able to come up with this mathematical system for doing things. And we're just kind of looking at it. We're just kind of like taking a big kind of historical view through it and looking at what they do to calculate a limit, to figure out what a function is doing. This is what we do, right? This is how you do it by hand. We've come to a point in modern day where in the real world, if you ever had to do a limit, you're going to go to a computer to do it. You're not going to do it by hand, right? You're not going to. because I want the bridge to work. Okay, I want the plane to fly. I trust the computer to get the answer more than I trust a human because the computer is not going to make the mistakes. But you still have to have somebody to program the computers, which means you have to have somebody that understands the theoretical part of the math. So, you know, you cannot just throw out everything theoretical and just be like, we'll just use computers. When I was in graduate school, that was one of the classes I took. Our project for the semester was to take three mathematical or engineering programs. It didn't matter. It just had to be something that was used in the real world, a computer program. And we basically had to, whatever the program was, we had to come up with a problem, okay, that we could find the theoretical, like, pure solution for. Okay, so we had to come up with this. We had to feed that through this program, whatever the program was, okay? And we had to have it come out with a mistake. We had to show that there's some computer program being used out there in the real world that we could feed it a problem where it would give a wrong answer, okay? And we could prove what the real answer was. So what we had to learn how to do in that class was to look at the program, find the weakness in the program, and exploit it. Does that make sense? So we call this the black box problem. What you don't ever want is an engineer building a bridge, going to a computer saying, give me the solution, taking that answer and building the bridge without there being some sort of check, somebody that knows the way that program was written, what its weaknesses are, what its strengths are, and that way you're getting correct answers. You cannot trust the black box. You have to understand how the black box works. Does that make sense? So we have to somehow keep the theory in here. We have to. All right. And this is a math class, not an engineering class. So, all right, I'm on my soapbox here. Let's get that. We only have 12 minutes left. How about I give you 5 minutes, just see what you can do? We're using the variable t instead of x. No big deal, right? It's just a different letter. Instead of x, we're using t. Doesn't change anything. See what you can do in 5 minutes with this. And yeah, we'll talk about it. Always check that you get 0 over 0. Do not assume you do. Always check. I just sent out a poll. I'm just curious if anyone has it done. If you don't, you don't have to put no, but if you have it, put yes. I'm just curious to see where we are. We'll go 2 more minutes. Okay, that's almost 2 minutes. All right, so I've started working this. And what I did at first, I saw it was 0, 0. And then I looked at some sort of factoring first, and I noticed that in the top, I could factor a t out, all right? So I had 3 people say that they got it. So I'm curious of somebody who thinks they got it, how they did it. Did you do this or do something different? No?
That's how I started with the factoring.
Okay. What did you do next? Did you leave this as 4 minus t and then do something, or did you do something with the 4 minus t?
I left that as 4 minus t, and then I did the conjugate.
You did 2 plus root t
Correct.
and then 2 plus root t, like that?
Correct.
Okay. Did it work?
That left me with
That should work. That should work.
yeah, my work's kind of messy, so I'm trying to find where that was.
So I'll show you. I'm going to continue with this. It works, but watch the way it works. It's tricky. Don't do anything on top, but foil out the bottom. So if you foil out the bottom, let's talk about what we get. 2 times 2, 4, right? What about the middle terms?
They cancel out.
They cancel. So don't worry about the middle terms. What about the last term? Negative root t times root t gives you what?
Negative t.
Negative t. Y'all see that? Do you see this?
Yep.
Yeah. And you're no longer going to have division by 0 because if t goes to 4, that's gone now. So you get limit t approaches 4. The only thing left here is t times 2 plus root t. And now at this point, let t go to 4, so no more limit. 4 times 2 plus root 4. Root 4 is 2, so this is 4 times 2 plus 2, which is going to be 4 times 4 is 16. Algebra, right? Algebra, weird algebra. What do y'all think of that?
When you do it, it's so logic, but I can't think about it by myself right now.
Yeah, right. So it's going to be a matter of like, at what point do you start being able to like do the algebra without having to have someone guide you through it, right? And so the practice is where that's going to come into play. I want to show you something else, another way of doing it. Actually, the way I would do it. This is not wrong. It worked. Okay, but watch this. Very unnatural move right there. What I did was I took the 4 minus t and I treated it like a difference of squares. So when you think about difference of squares formula, difference of squares says this: a squared minus b squared is a plus b times a minus b. You learn that in algebra. So if you look at 4 minus t in an algebra class, we would never look at that as being a difference of squares, not in a regular algebra class. But in calculus, you actually can look at that as being 2 squared minus the square root of t squared. I know it's weird, but 4 is 2 squared. And if I take the square root of t and square it, I get t. So it's like, this is my a and this is my b. And so this formula will work. I just replace that with 2 plus root t, 2 minus root t. And it's the same thing. And see, what's nice about doing it this way is that that cancels right away. And now you've got this, which is the same as this piece right here. Okay. All right. So here's the deal on the homework. Here's what I would like you to do for the homework. All right. Forget what this says on the schedule for right now. All right. Right now it says to do all these problems for 1.4. All right. Here's what I want you to do instead. I want you to do, this is 1.4, okay? I want you to do problems 11 through 28. Now, all of these problems are problems that I've done like today. They're just limits, and you're supposed to figure out what they are by hand, all right? I recommend that you start by doing the odds, okay? So you can at least find the answer. I've done a lot of these on video already. And then once you've done that, do the evens. But I recommend, encourage, stress that you should do all of these problems. Like we're at a point in this class where, for sure, from here on out, if you can't do this part, the rest of the class can be hard. All right. So we got to get all this algebra down and get comfortable with it and all that. Get to a point where you feel confident when you're presented with a limit. All right. So let's let that be the homework assignment. And then I'd like to offer a bonus. And I know I'm out of time, so if you need to leave, you can leave. All right. You're free to leave, and you can just watch the video later on this. But the bonus, what I'd like to do is talk about this problem that I sent out to everyone. All right. So this problem, talks about you're trying to lay fiber optic cable from building A to building B. We're trying to figure out how to come up with a competitive bid. So here's the bonus. you have to use the discussion board, or you can use the chat here right now if you'd like. It doesn't matter. I'd like for you to form a group of anywhere between 2 to 4 people. No less than 2, no more than 4. And what I want you to do is, with this problem, I want to see if any group can come up with a formula that gives me the cost of doing this project. I want to see as a group what you can come up with. So I'm going to type it down here. What I want a function, okay, a function of a single variable which gives the cost of installing the cable. Now, if you don't understand what I'm asking for, I'm hoping that in a group you can figure that out. And I'm open to you asking me questions, you know, as after your group talks, you say, okay, hey, here we have some questions, we're unsure about this, or hey, how does this look? And there's no due date for this, all right? But the way I'm going to do it is if groups start to get the answer or get something, the first group done is going to get the most points, and then from there on out, it'll taper off. And if only one group gets it, you get the most points. And this will be a bonus that'll be added to one of your exams. I'm not sure when, whether it's exam 1 or 2 or 3. All right. So this is not something that has really a lot to do with limits or anything like that. This is just a more broad topic in this class. We are going to have to do this problem later on. Like, we're going to have to solve it. So I want you to start thinking about it. Do y'all understand? Form a group, however you want to do it. And then y'all can set up a time, y'all can meet and talk or whatever y'all want to do. And then what you'll do is, as a group, you'll submit just one paper with all of your names on it and say, here's what we did, and explain it to me. Make sense? Do you all want me to just randomly throw y'all into groups right now? Or are you going to do it on your own? You care?
I'm already doing one.
You already got it? Okay. I'll let y'all handle it. You're all adults. Okay. Do your homework for 1-4 and get with me in my office hours if you need help. And when we come back, expect a quiz on Thursday. All right. Work hard. Have a good day. I'll leave the session open if y'all want to chat with each other or anything.